Let's revisit refraction, the idea of a light ray bending as it passes from one medium to another. We're going to, in this process, figure out a way of keeping light inside a material, a process that has ramifications for our modern technologies. Remember when we looked at refraction, it turned out that by changing speed, the light ray changed its direction as it went from one medium to the next. On the slide we have here, you can see the ray is actually now going from a medium N1 into a medium N2 that is a smaller refractive index. That means, remember, the wave is speeding up. And unlike before, where the refracted ray bent closer to the normal, now the refracted ray bends away from the normal. The relationship between those angles, θ1 and θ2, is given by Snell's law at the bottom of the diagram. Now θ2 will always be larger than θ1, so if we increase θ1, we'll be increasing θ2, and we'll get to a point where θ1 has become so large that θ2 will equal 90 degrees. That means the refracted ray is going to be running along the interface. Let's not forget, we'll also have a reflected ray the whole time. Whenever we have a bent ray, we also have one obeying the law of reflection. Now, what does a refracted ray along the interface mean? Well, it can't really exist. The ray either has to be in a medium with N1 or a medium with N2. So in fact, at that point, the refracted ray disappears. We call this the critical angle, θc. The critical angle is when θc is when that refracted angle θ2 equals 90 degrees. And using Snell's law, we can see that that critical angle will therefore be the inverse sine of N2 divided by N1. Now, for values like going from glass into air, that's an angle of around 40 degrees. So any angle that is larger than that for the incident ray in the glass, it can't escape the glass. It gets trapped in, and in fact all you have is the reflected ray. We call this type of refraction where there isn't a refracted beam, we call this total internal reflection. And that should be a fairly obvious name. Instead of refracting, all of the beam stays inside the material and reflects from the interface. In a sense, what we've done is we've turned that interface between the two materials into a mirror. And there are some useful examples where this is quite a nice technology to use. One is to, instead of using a mirror, you can use a prism where a light ray comes into the prism, normal to the first surface, meets that second surface at an angle larger than the critical angle, and will be totally internally reflected. And we've actually used that interface there, that glass-to-air interface, for example, as a mirror. And this finds applications, for example, in turning a telescope into something more compact like a set of binoculars. You want to fold the light up inside, and making it bend around using prisms is a very useful way to do that. Another way we might consider this is if we had, for example, a glass rod. Here's a diagram indicating a glass rod, and if we had some light travelling inside that glass rod that made an angle larger than the critical angle with the normal to the surface, then it would be totally internally reflected. It wouldn't bounce out from inside the glass, it would stay within the glass. In a sense, this light ray has been trapped by total internal reflection in our rod. Now, what our rod is really indicating here is the kind of device we call an optical fibre. An optical fibre is a very, very tiny version of this, but of course light can fit into quite small spaces. Its wavelength is absolutely tiny as well. And this is the start of the technology we call fibre optic technology, using total internal reflection to keep the light trapped inside the material. Now, we are a bit concerned about the interface between the inside and the outside, so rather than relying upon, say, glass to air, we'll normally put some kind of cladding on the outside. We still need to make sure we understand the refractive index of the cladding versus the refractive index of the inside of the fibre. One of the nice things about an optical fibre is you can now maybe bend or change this shape from being a straight line, and again, the light that is trapped inside using total internal reflection will still remain trapped inside even at the bend, provided the bend isn't so great that the angle in there becomes smaller than the critical angle. And so in fact, if you bend an optical fibre too much, some light will start to refract out, and we call that bending loss. Now, this idea of piping light around is really at the heart of so much of our information and communication technologies these days. sending information, particularly using laser light, down optical fibres has become the basis upon which we do so much of our everyday life, using telephones, using the internet, all kinds of abilities. It's actually easier to put information down one optical fibre than it is down tens or hundreds of copper cables using electrical current. So that finishes now with the total internal reflection idea. In fact, for now we're going to take a break from doing ray approximation with our optics. In the next topic, we're going to go back and remember that our light really is a wave and look at some of the wave properties that give us some strange behaviour of light.